You're up for some more chemistry, right? Well then, let's just dive right into oxidation numbers today. What are oxidation numbers, what do you need them for, and how to spell the damn word? This will all be revealed in this video. Right, so what the clickety-clack is an oxidation number? Oxidation numbers are really important when you want to set up redox reactions. This is because when it comes to redox reactions, they can help you figure out which partial reaction takes place as oxidation and which as reduction. Here's a little pro tip. If you just haven't got the faintest idea of the term oxidation and reduction, perhaps you should check out our video on exactly that topic. If you want to be able to set up really complicated redox reactions, then you need oxidation numbers. And how do I know what the oxidation number of each atom or molecule is? Great question. Here's the answer. Luckily, there's a list of rules for that. Let's go through the individual rules one by one. Rule number 1. If you add together the oxidation numbers of the individual atoms of a molecule, you will always get the molecular charge. For example, for neutral water, it looks like this. The water molecule has a molecular charge of 0, which means the sum of the oxidation numbers also has to be 0. As another example, if we add an H3O plus ion, the charge would be +1. Then the sum of the oxidation numbers would also have to come to +1. From this, we can derive two more rules. Rule number 2. If we have elemental molecules or just individual neutral atoms, their oxidation numbers are always simply 0. It then makes sense, of course, that sodium or hydrogen are electrically neutral, and therefore the oxidation number is also simply 0, just like the charge. Now for rule number 3. When it comes to monoatomic ions, the oxidation number is just the charge number. With Na+, the oxidation number would be a nice flat +1. This follows simply from the first rule. Of course, the sum of the oxidation numbers should be given the charge, and if the charge is +1 and we only have one atom, then that atom also has to have an oxidation number of +1. For S2-, it would then simply be -2. So far so good, right? So let's keep going. Rule number 4 deals with hydrogen. The oxidation number of hydrogen depends on the other elements that it bonds with. To keep it nice and simple, with nonmetals, the oxidation number is always +1. And with metals, it's simply -1. Rule number 5 only affects fluorine. You should probably go and make yourself a cup of tea because fluorine takes some time to understand. We'll try to summarize in a manner that's clear and simple. When fluorine forms a bond, it always, and I do mean always, has an oxidation number of -1. Ooh, that was tough. Let's move on to number 6. Oxygen almost always has an oxidation number of -2, with a couple of small exceptions. In peroxides, such as hydrogen peroxide, oxygen has a value of -1. And also, when it bonds to fluorine, Rule 5 takes center stage. In O2F2, fluorine always has -1, as you know already, and so oxygen must have a corresponding value of +1. But then, you can of course work that out easily by using the rules. Cool, that's all the rules covered already. Are you still with us? Great! In that case, we can now take a look at a couple of examples. Let's see if these rules are useful for anything. For our first example, let's take the hydroxide ion OH-. Rule 4 tells us that hydrogen with a nonmetal has an oxidation number of +1. And from Rule 1, we know that the sum of the individual oxidation numbers has to be the same as the charge of the molecule or ion. The ionic charge of a hydroxide ion is simply -1. Okay, so let's work it out. The sum of the oxidation numbers for oxygen and hydrogen must equal the charge of -1. Let's solve that for oxygen. Hydrogen is simple, it's +1, so let's just substitute that in. -1 minus 1 is obviously just -2, and in the end, we find the oxidation number of oxygen is -2. By the way, we could also have determined the oxidation number of oxygen by using Rule 6. Hydroxide is not one of the exceptions to this rule, so we could have just looked it up to find that the oxidation number of oxygen has to be -2. Great, let's cook up another example. Fe2O3 or iron 3 oxide. From Rule 6, we know that oxygen must also have an oxidation number of -2 here, and the molecular charge is 0. But now how about the iron? Let's just work it out. 2 times the oxidation number of iron plus 3 times the oxidation number of oxygen has got to equal the molecular charge. And here we're solving for iron. If we fast forward through that, it looks like this. Oxidation number of oxygen is -2. 3 times 3 gives -6. That comes over to the other side and becomes +6. Now divide by 2 and that gives +3. Make sure to pay attention here to the fact that we have more than one atom of both iron and oxygen in our compound. Awesome, so we've cleared that up as well. Now, here's a summary to see you on your way. We need oxidation numbers for redox reactions, and we can figure them out by following 6 simple rules. So here's a short overview of the 6 rules. These are some really lousy exercises to suffer through sometimes, but you should definitely practice them anyway. Otherwise, we can guarantee you'll be tearing your hair out when it comes to redox reactions. So save yourself the pain and learn this stuff properly. Then you'll have nothing to fear. See you guys!